Okay, suppose that we have a film of soap, like a bubble. Okay, so this would be like a soap bubble, but we're just looking at one piece of it, just so it's just like a thin film of soap just sitting in air. So we've got air and soap, and suppose we have some light, sunlight, or just one particular array of light that's coming in, and it enters the soap film. Well, soap slows light. Lots of materials slow down light. Any material that light can actually get through slows it down. And we need to describe how does the light slow down, how much. Okay, so if we were to say that in air, or even better in vacuum, okay, the speed that the wave travels is c, 3 times 10 to the 8th meters per second. Okay, and air is not too much different than vacuum. Okay, it doesn't slow down light very much at all. So we can often just think air and vacuum are the same. Okay, when it enters, it's going to travel at a slower speed. Okay, so it's going to keep on going. We'll call it speed v. All right. Now, because it's moving at a slower speed, the wavelength must change. Because remember, out here, we have c equals lambda f, and I'm going to put a 0 here, meaning it's our vacuum wavelength. It's a wavelength that we would have in vacuum or in air. Again, very close. But over here, we're going to have v equals lambda f, and that I'll leave it unsubscripted. It's the wavelength in the material, in the soap film. So when we think about that, we're like, okay, well, how does the wavelengths change? Well, if it slows down, we know the wavelength should get smaller because the frequencies don't change. That's a property of the source. Whatever caused this wiggle, that frequency is not changing. It's going to go up and down the same number of times per second. But if it slows down, then those up and downs get scrunched closer together. So we get a shorter wavelength. And then it would come back in air and it would extend back out long again. Okay. So when we're thinking about interference, it's really important to know what is the wavelength of that light in the material. Okay. And so we need to find this lambda in terms of what we know it is in vacuum. Okay, well, we define a certain variable, n, called the index of refraction. And we're going to get into that variable much more when we talk about light later on. But that index of refraction is a ratio of the speed in vacuum over the speed in the material. Okay. So let's go ahead and take this, and that's a number that we can look up, or measure for a new material. We can measure that. Okay. So let's go ahead and divide this by this. So we have that is lambda 0 f over that, which is lambda over f. Since the frequency is the same, okay, those cancel out. And so I can find this wavelength in the material, knowing the wavelength in vacuum. Just multiply that up, multiply that down. I get lambda equals the original wavelength divided by this number, this index of refraction. Okay. So that is now a way we can think about the wavelength. How much did it change? And we'll use that later on.